So we begin with Laplace transforms. These are used to solve differential equations, ordinary differential equations in a very elegant manner, very elegant and very efficient manner. We can solve differential equations. But before that, we have to learn the formulae for Laplace transforms and the inverse transforms. Then we can apply it for differential equation. So this discussion on Laplace transforms will be divided into three parts. First, we discuss the basic definition and finding of the Laplace transforms. Next, the inverse transforms. And then finally, application to differential equations. So the formula list is similar to that of derivatives and antiderivatives type. So we have to learn the formula list. So let us first begin with the definition. So the definition of Laplace transform. So let f of t be a function of t defined for all positive values of t. Then the Laplace transform of f of t is defined by or is defined as L of f of t. This is the Laplace transform of f of t. It is defined by this integral 0 to infinity e power minus st times f of t dt, where of course the integral should exist. Otherwise, if integral doesn't exist, we say that Laplace transform doesn't exist. Now, where s is a parameter, real or complex, it is some parameter. So this is the definition of the Laplace transform. It is integral Laplace transform of a function is integral 0 to infinity e power minus st f of t dt. Now, so Laplace transform of f of t, see, by definition, what happens when we integrate with respect to t and we are substituting the limits for t. So s remains. So what happens is this remains a function of s. So Laplace transform f of t is a function of s and is written as f bar of s. So f bar of s, when we write, it means that this is the Laplace transform of f of t. So we write like this. It's a function of s. Laplace transform of f of t is f bar s. Now, we can also find f of t like this. Suppose we know f dash. So we can also write f of t as the Laplace inverse transform of f bar s. So this is called as the inverse Laplace transform. So f of t is called as the inverse Laplace transform of f bar s. Okay. So this L written like this is called the Laplace transform operator. So a function of t is being transformed to a function of a parameter s. So that is the Laplace transform. So Laplace transform of f of t is defined as integral 0 to infinity e power minus st f of t dt. So this is a function of s. So Laplace transform of a function defined in terms of t or x, it is converted to another parameter s. So it has been transformed. And then this f of t can be written as the inverse Laplace transform of f bar of s. So this is very, very useful, these operations, in simplifying the differential equations. It converts the differential equation just into a simple linear algebraic problem, which we can easily solve. Now, we have to have the standard Laplace transforms. So transforms or Laplace transforms of elementary functions. We have to memorize this list. It's an important list. First, Laplace transform of 1 is 1 upon s. S must be greater than 0. Very important. So substitute here. If the function is 1, integral of e power st dt. So it is e power minus st by minus s from 0 to infinity. So when you substitute infinity, you get 0, provided s is greater than 0. And minus e power 0 is 1, so upon s. So you get 1 by s for the condition s greater than 0. If s is not greater than 0, Laplace transform of 1 goes to infinity. So that's why this is the basic condition we put, that s should be greater than 0. It's just a matter of applying integral. Next, Laplace transform of t power n. So this was 1, that is t power 0. Now t power n is n factorial by s power n plus 1. So in this, you put n equal to 0, we get the first relation. Okay. Now this, because it is n factorial, this is valid only for n being whole numbers. It is not valid for negative integers, n being a negative integer or n being a fraction. Next, Laplace transform of e power at for an exponential function. It is 1 upon s minus a. Very simple. We can do the integral. We will get that. Condition, of course, s should be greater than a. That means this has to be positive. S has to be positive here. S minus A has to be positive here. Laplace transform of sine 80 is A upon S square plus A square. Then Laplace transform of cos 80 is S upon S square plus A square. In all these cases, of course, S greater than 0, this condition is important. Next, Laplace transform of sine hyperbolic 80 is A upon S square minus A square. And because this S square minus A square, here S has to be greater than modulus of A. Because A can be a negative quantity, so S has to be greater than modulus of A. Now, cos h hyperbolic 80 is S upon S square minus A square. Again, S is greater than modulus of A. The idea is the denominator has to be positive. So these are Laplace transform of 1 is 1 by S. Laplace transform of t power n is n factorial by S power n plus 1. Laplace transform of e power 80 is 1 by S minus A. Laplace transform of sine 80 is A upon S square plus A square. Laplace transform of cos 80 is S upon S square plus A square. Laplace transform of sine hyperbolic 80 is A upon S square minus A square. Cos hyperbolic 80 is S upon S square minus A square. So these are some basic transforms. We can just prove this just by integration. It's not a difficult one. All of these, we just have to remember these. Now, these are the elementary one. Now, properties of Laplace transform. Properties of Laplace transform. First is the linearity property. So linearity property. Suppose Laplace transform of three functions in linear combination. F of t, g of t, and say h of t. This will be, coefficients will come out. It will be Laplace transform of f of t plus b times Laplace transform of g of t plus c times Laplace transform of h of t. So this is just like our integrals and differentials. This is linearity property. Next is the first shifting property. This is a very useful property which we'll use very often in problems. This is also called as the S shifting property. Now what it says is this: if Laplace transform of f of t is f bar of s, then Laplace transform of e power 80 times f of s is f bar of S minus A. It's f bar of S minus A. This is a very simple proof. We know proof is very simple. Laplace transform of f of t is integral 0 to infinity e power minus st into f of t. Now you get a function for this. Now if I introduce this one e power at f of t, so I get integral 0 to infinity e power minus st into e power at f of t. Now a is a constant. We are integrating with respect to t. So we can always write this as e power s minus a f of t dt. So what you get, you can replace s minus a by some b, and then you will get this is same as this function. Instead of s, you have b. So you will get a Laplace transform in terms of b. Now that b is s minus a. So f bar b and b is s minus a. So this is what you get. So this is a very useful property and associated useful results. In all these cases, S is greater than A. All right, associated useful results. Now, we know that Laplace transform of 1 is 1 by S. So Laplace transform of 1 times e power at will be 1 by S minus A. So we know that and we got this. Now Laplace transform of t power n we know. Now e power at t power n will be n factorial by, it was s to the power n plus 1. Now we'll get s minus a to the power of n plus 1. S minus a to the power n plus 1. Third, Laplace transform of e power at and sine bt. Sine bt was a by s square plus a square, or uh, so now this is a, this is b. So we get b by s square plus b square, that s should be replaced by s minus a. So yeah, sine 80 was a by s square plus a square. Sine bt will be b by s square plus b square. Now to that, if e power 80 is multiplied, the function, then it becomes b by s minus a whole square plus b square. Then Laplace transform of e power 80 cos bt will be s minus a, s by s square plus b square. So s minus a into s minus a whole square plus b square. So extending this to sine hyperbolic and cos hyperbolic, you have b by s minus a whole square minus b square. S minus a by s minus a whole square minus b square. Okay, so just transformation. So this is called as S shifting property. That means the function has shifted from s to s minus a, like that. Next is change of scale property. Third one. B, C. This is change of scale property. So if Laplace transform of f of t is f bar of s, then Laplace transform of f of at. Now it is not multiplication outside, it is multiplication of the parameter f of at. Here you will get 1 by a f bar of s by a. So this is called as the change of scale property. Okay. We can do this. We can show that put at as some x, and by substituting we can show this. It's not a difficult proof. Then we have this second shifting property. This is also called as, that was S shifting. This is called as T shifting property. So if Laplace transform of f of t is f bar of s, and if this and if there is another function f1 of t is such that it is f of t minus a for all t greater than a, and it is 0 for all t less than a. So what, this is the original function, but now original function, if the function is greater than a, then at a it will be f of 0, at a plus 1 it will be f of 1. So the whole function has been shifted along the x-axis. So this function t minus a by a units, and below that if t is less than a, it is 0. So it is like a step, or just shifting the function. So for such a function, if for such a function, what will be the Laplace transform? Okay, here a has to be greater than 0. Very important. So then Laplace transform of this function f of t, which is f of t minus a and 0, this will be equal to e power minus as times f bar of s. Now this is not s minus a, but this is e power as comes outside. Okay, so these are the 4 properties that we have for Laplace transform. Now we will one by one try to apply these properties and solve problems. Some basic problems for practice. So first type is find the Laplace transforms of the following functions. So the first one function is sine 2t, sine 3t. Okay. So how to do this? Now we know for sine t and cos t, but we don't know for a product. So natural logic is convert the product to sums. Sine c, sine d formula. So f of t, which is sine 2t and sine 3t, will be equal to 1 by 2 times 2 sine c sine d is uh, cos of a minus b minus cos of a plus b. So cos of a minus b is cos of 2t minus 3t is cos of minus t, which is cos t, minus cos of a um, plus b. So cos of 2t plus 3t, it will be cos of 5t. So just basic trigonometric formula. Therefore, Laplace transform of f of t is the transform on this whole thing, which becomes, using the linear property, half of Laplace transform of cos t minus half of Laplace transform of cos 5t. So this is half. Now s upon s square plus a square for cos. Let's go there. Cos 80 is s upon s square plus a square. So a here is 1 in the first case. So we get s upon s square plus 1 square minus half s upon s square plus 5 square, that is 25. So taking half common, or s upon 2 common, we get s square plus 25 minus s square minus 1 upon s square plus 1 into s square plus 25. Just removing the partial fractions, s square cancels. 25 minus 1 is 24 upon 2 is 12. So we get 12s upon s square plus 1 into s square plus 25. So the Laplace transform of this function, this f of t, sine 2t, sine 3t, it has converted to a function, algebraic function of s. So this is how we find the Laplace transform. Okay, next, let us do this function. E power 2t plus 4t cube. So there are multiple functions involved here. 2 sine 3t minus 2 sine 3t plus 3 cos 3t. So we need to find the Laplace transforms. Laplace transform of this function. So Laplace transform of this function f of t is transform of e power 2t plus 4 times transform of t cube minus 2 times Laplace transform of sine 3t plus 3 times Laplace transform of cos 3t. And we apply. E power 80 transform is 1 upon s minus a. So 1 upon s minus 2 plus 4 times Laplace transform of t power n is n factorial by s to the power n plus 1. So we get n factorial, that is 3 factorial by s to the power 3 plus 1, 4, minus 2 times sine 3t is 3 upon s square plus 3 square plus 3 times cos 3t is s upon s square plus 3 square. Now let us simplify this. This is s power 4. So we have 1 by s minus 2 plus 6 fours, 24 by s power 4. And we can take 3 common here. 3 times s minus 2 upon s square plus 9. So this is the Laplace transform of the function. So just applying the concepts. Okay. Next, one more. Now f of t is cos at plus b. So how to approach this problem? We know cos at, we know sin at, but we don't have, cos of at plus b. So first of all, before using the transform, we can simplify. F of t is cos of at plus b, which is cos a, cos at, cos b minus sin at, sin b, cos of a plus b formula. So this is a constant and this is a constant. And these are functions of t. Now we can apply Laplace transform of f of t will be cos b times Laplace transform of cos at minus sin b times Laplace transform of sin at. So this will be cos b times s upon s square plus a square. Now minus sin b times a upon s square plus a square. Therefore, Laplace transform of this function will be s cos b minus a sin b by s square plus a square. This is the transform function. So it is just a matter of algebraic and trigonometric manipulations. It is not difficult. Next. F of t is t minus sine hyperbolic 2t. So 1 on hyperbolic we are introducing. So solution. Laplace transform of f of t is Laplace transform of this function t minus Laplace transform of sine hyperbolic. So t power n is n factorial by s power n plus 1. So t power 1 becomes 2 factorial by sorry, it becomes 1 factorial by s square. And this is 2 by s square minus 2 square. So it is 1 by s square minus 2 upon s square minus 4. And this can be simplified s square minus 4 minus 2s square by s square into s square minus 4. So upon simplification, we get uh, minus of s square plus 4 upon s square into s square minus 4. This is the Laplace transform. Now second set, now using properties, let us see. These were basic problems on Laplace transform. Now the second set, find the Laplace transforms of the following functions. I'll to continue the numbering, I'll write as 5. Okay, it's not 5, it is within this category, it is the first one. So let's say f of t is t cube into e power minus 3. So see, we know Laplace transform of t cube is n factorial by s power n plus 1. So this is the one. Now Laplace transform of e power at times t cube. So in this, we have to do s minus a. So we'll get 3 factorial by s minus of minus 3, s plus 3 whole power 4. A is minus 3 here. So remember, so s minus a becomes s plus 3 whole power 4. So you get 6 upon s plus 3 whole power 4. This is the Laplace uh, transform for this function. This is using the s shifting property. Okay, one more. F of t is e power minus t sine square t. What should we do now? First of all, this has to be simplified. We don't have a standard formula for sine square t. So what we need to do? First simplify this. Now e power minus t sine square can be written as 1 minus cos 2t upon 2. So this is half e power minus t and half e power minus t cos 2t. Therefore, now Laplace transform of f of t will be half Laplace transform of e power minus t minus half Laplace transform of e power minus t cos 2t. Now this is the standard formula, 1 upon s minus a. So my a is minus 1. So we get s plus 1. Next, minus half. This is cos 2t. Cos 2t will be s upon s square plus 2 square. Now this s has to be replaced by s minus a using shifting property. Cos 2t Laplace transform is s upon s square minus s square plus 2 square. But we are multiplying with e power minus t. So s has to be replaced by s minus a, s minus of minus 1. So s plus 1 by s plus 1 the whole square plus 4. So this is the method. So we can simplify this further if we want. This is s square plus 2s plus 1 plus 4, 5 minus s plus 1 the whole square. Oh, s square plus 2s plus 1. So we are left with everything cancels. We are left with 4 by 2, which is 2. So this is the Laplace transform. Important problems. Next, f of t is cos hyperbolic 80 times sine 80. So solution. Now, first of all, this hyperbolic cos sine hyperbolic 80 is e power e power 80 minus e power minus 80 by 2. Sine hyperbolic x is e power x minus e power minus x upon 2. So cos hyperbolic 80 will be e power 80 plus e power minus 80 by 2. This is the definition of hyperbolic functions. So cos hyperbolic can be written like this: e power 80 plus e power minus 80 by 2 sine 80. So now this can be split into two functions: e power 80 sine 80 plus half e power minus 80 sine 80. Therefore, Laplace transform of f of t is half Laplace transform of e power 80 sine 80 plus half Laplace transform of e power minus 80 sine 80. Now, this is simple, s minus a. So you get a upon s minus a the whole square plus a square. This a by s square plus a square multiplied by e power 80. Now this is plus half. Again, a by, instead of s minus a this time, it is s minus of minus a, s plus a the whole square plus a square. Now, if we simplify this, see how it looks. This simplification is also important because while we do inverse transform, we will come across this s square plus 2a square minus 4as. S square plus 2a square plus 4as. See, now a by 2 taken common, you will see, because it is plus s square plus 2a square plus 4as plus s square plus 2a square minus 4as by a minus b into a plus b. A uh, a minus b into a plus b for oh sorry, this is 2as 2 2as 2as. So this becomes 4a square s square. Now this cancels, 2as and minus 2as cancels. This is twice of it, that gets divided by 2. S square plus 2a square upon. This is s power 4 plus 4a power 4 plus 4 a square a square. That's plus 4 a square and minus 4 a square cancels. And we are left with s power 4 plus 4a power 4. Such a complicated expression turned out to be something so very simple. Now, so when we do an inverse transform, you can see that although this function seems simple, its inverse transform will involve hyperbolic terms. Okay. Okay. Now, another one. Very important result. This is 5, 6, this is 7. And then 8th one, this is a very important one. Show that Laplace transform of t cos 80 is s square minus a square by s square plus a square whole square, and Laplace transform of t sine 80 is 2as upon s square plus a square whole square. This is a very important result. And it is important to say at one go we can prove both. How to do? So first find for t Laplace transform of t is 1 factorial by s power 1 plus 1 s square. Now consider this e power I at complex. This will be cos 80. This is the Euler's formula for complex numbers, Euler's representation. Cos 80 times I sin 80. E power I theta is cos theta plus I sin theta. So we are using that. So when we do this, now uh, t times e power I a t is t cos 80 plus I t sin 80. Therefore, Laplace transform of t times e power I a t is Laplace transform of t cos 80 plus I times Laplace transform of t sin 80. Now what's happening here? So the real part, so this is nothing but the real part of the left hand side, and this is nothing but the imaginary part of the left hand side. Therefore, we get Laplace transform of t cos 80 is the real part of Laplace transform of t e power I a t, and Laplace transform of t sin 80 will be the imaginary part of Laplace transform of t e power I a t. So this simplifies very, very easily. Therefore, now all problem rests in finding this t power e I a t. So Laplace transform of t is 1 by s square. Now when you multiply with e power 80, 1 by s minus a whole square. So here you get 1 by s minus ia the whole square. This is what it is. Now we have to split into real and imaginary parts, this one. So this simplifies to 1 upon s square plus I square a square will give me minus a square minus 2ias. Now I multiply and divide by the conjugate of this s square minus a square plus 2ias, s square minus a square plus 2ias. I'm just multiplying with the conjugate. So I get s square minus a square plus I times 2as upon s square minus a square the whole square plus 4a square s square. When you look at the denominator, this is a minus b the whole square plus 4ab. The denominator becomes, you can expand and see, s power 4 plus a power 4 minus 2 s square plus 4 s square becomes plus 2 a square. So we get the denominator converts to s square plus a square the whole square. So now solved, the real part is s square minus a square by s square plus a square the whole square plus the imaginary part 2as by s square plus a square the whole square. Okay. So this is 1a, this is 1b. So from 1a and 1b, we get Laplace transform of t cos 80 is s square minus a square upon s square plus a square the whole square. Laplace transform of t sine 80 is 2as upon s square plus a square the whole square. A very important proof. Okay. Next, we have this um, Laplace transform of derivatives and integrals. There are four more important properties. These are very important properties, extremely important properties. So we had A, B, C, D earlier in properties. Okay, we can write 4A again. Those were dealt with, shifting and other things. This is further very, very important. So if Laplace transform of f of t is f bar of s, then Laplace transform of t times f of t is minus derivative with respect to s of this function, the Laplace transform of f of t. So if you multiply by t, you have to differentiate. Now, in general, okay, this is in general, Laplace transform of t power n f of t will be minus 1 to the power n nth derivative with respect to s of the Laplace transform of f of t. So the more you multiply with t, so many times you have to differentiate the transform. The proof of this is very, very simple. It is not a difficult one. So in fact, it's a very simple proof. I'll not do for everything, just so that we get the confidence of this. So we know that Laplace transform is integral 0 to infinity e power minus st f of t dt. Now if I differentiate this with respect to s, so this is with respect to t. When I differentiate it partially with respect to s, I'm not going to differentiate with respect to t because it is with respect to s. So what we get is integral 0 to infinity minus t. We are differentiating with respect to s, mind you, so t will be like a constant, e power minus st. f of t dt. So this is minus integral 0 to infinity e power minus st into t times f of t dt. So this is Laplace transform of t times f of t. So therefore, Laplace transform of t times f of t is equal to minus of the first derivative of f dashes. So continuing like this, we keep differentiating. Each time we differentiate, we another factor of t comes out, and that's why uh, if it is t power n, there will be n derivatives. It's an important property. So this is like multiplication by t. This property is called as multiplication by t power n, or multiplication by t. Second property in this type is division by t. Now, if Laplace transform of f of t is f bar s, then this is interesting. So if multiplication by t, you have to differentiate. Then if it's a division by t, then we'll have to integrate. So division by t, it is integral from s to infinity, integral from s to infinity of the Laplace transform of s. So again, we can show this. It's uh, we can do a double integral change of order, and you can show this. Okay, I leave it. I don't go into the proof over here. Then further, Laplace transform of derivatives and Laplace transform of integrals. This is very important, very, very important properties from the point of view of differential equations. Laplace transform of derivatives. Laplace transforms of derivatives. First, if Laplace transform of, okay, we'll change the color. If Laplace transform of f of t is f bar s, then first part, Laplace transform of the first derivative of t, f of t, will be s into f bar s minus minus f of 0. S into f bar s minus f of 0. Second, now Laplace transform of f power n is nth derivative. This is not power n, this is nth derivative. So it is s power n f bar s minus s power n minus 1 f of 0 minus s power n minus 2 f dash 0 minus s power n minus 3 f double dash 0 up to. So always it starts with this, and then again second derivative, third derivative, and so on. So we can show this. It is just by the integration formula, but we just need to remember this one. This, it's a very, very important one. F bar s minus s power n f bar s minus s power n minus 1 f of 0. Keep reducing the powers of s after that, and keep increasing the order of the derivatives. Substitute at s equal to 0. So this is the Laplace transform of derivatives. Then we have Laplace transform of integrals. Now, if Laplace transform of f of t is f bar s, so in derivatives, we multiplied f bar with s. So now if it's an integral, then Laplace transform of integral 0 to t f of u du function. See the limit 0 to t, very important, an integral of this, then it will be 1 by s f bar of s. 1 by s f bar of s. So these are some important, uh, these are the four very important properties: multiplication by t, division by t, and then transforms. Few problems we'll do, and we'll continue in the next week. Multiplication and division, we'll do that first. Multiplication, a number of ones. Find the Laplace transforms of the following functions. Now the first one, this, okay, let's write this as the first. F of t is t cos at. Just now we did by one process. Now let us, we multiplied by e power I at and so on. Now let us look at this. Laplace transform of t cos at is minus d by ds of Laplace transform of cos at. So minus d by ds, Laplace transform, it is s by s square plus a square. So this becomes s square plus a square the whole square, and s square plus a square times 1 minus s times 2s. Differentiating u by v rule. So we get a square minus s square. So this with a minus sign, it becomes s square minus a square by s square plus a square whole square. Is the same thing we got by that method, multiplying by e power iat. Okay. Second, let us now do, we'll not do t times sine, we'll do t square times sine. So we need to do a double differentiation. T square sine 80, which is minus 1 the whole square second derivative with respect to s of the Laplace transform of sine 80. So this is d square by ds square of a by s square plus a square. So first derivative. So first derivative gives a upon s square plus a square the whole square with a minus sign multiplied by 2s. Okay. Now the second derivative will be s square plus a square the whole power 4. This minus sign kept aside. S square plus a square the whole square into derivative with respect to s 2a minus when 2as times this 2 times s square plus a square into 2s. Just u by v rule. Ah. So s square plus a square, this s square plus a square cancels. We'll get s square plus a square 2a we can take common. S square plus a square minus 2a we take common. This cancels. Then you have 4s square minus 4s square times 2a. Okay, so we get s square minus 4s square is minus 3s square with a minus sign. Take this inside. 3s square minus a square multiplied by 2a divided by s square plus a square whole cube. So this is the answer. Okay. So it is just a matter of differentiating. F of t is t e power minus t sine 3t. So now there are two rules. One is, the shifting property is applied on this, and then this differentiation property is applied. Integral, sorry, Laplace transform of f of t is Laplace transform of t e power minus t sine 3t, which is minus d by ds of Laplace transform of e power minus t sine 3t. So this is minus d by ds. Now we have to apply the shifting property here. 3 by s square plus 3 square. This s will be replaced by s minus a. A is minus 1. So s plus 1 the whole square plus 3 square. Now we need to differentiate this one. So minus times minus 3 by s square plus 2s plus 10 the whole square times, I'm differentiating this minus 1 into minus 3, 2s plus 2. So minus into minus becomes plus. So we get 6 of s plus 1 by s square plus 2s plus 10 the whole square. So this is the Laplace transform by using differentiation. Now let's do a few examples on integration. Now I need to find Laplace transform of this function 1 minus et divided by d. So first what I'll do is Laplace transform of 1 minus et is Laplace transform of 1 minus Laplace transform of e power t. This is 1 by s minus 1 by s minus a, that is s minus 1. Now, if I have to do Laplace transform of division by t, this becomes integral s to infinity of this Laplace transform of 1 minus e power. Okay. ds, sorry, this will be s. So it is integral of this transform. So we get log of s minus log of s minus 1. So I get log of s by s minus 1. So this is the Laplace transform. One more on integrals. F of t is cos at minus cos bt by t. Now Laplace transform of cos at minus cos bt is Laplace transform of cos at minus Laplace transform of cos bt. This is s by s square plus a square minus s by s square plus b square. Now I need to find Laplace transform of cos at minus cos bt upon t. This becomes the integral from s to infinity of the Laplace transform of the numerator. This one, cos at minus cos b. So multiplication by t and then division by t. So this integral is, log of half multiply and divide by 2. So numerator is the derivative, denominator is the function f dash x by f of x form. So half log s square plus a square minus half log s square plus b square from s to infinity. So half, this is like a improper integral. From s to infinity. So when s approaches infinity, this is infinity upon infinity. You can divide by a square, you will get log 1. So you will get log 1 minus log of s square plus a square by s square plus b square. Log 1 is 0. So then we have half minus half log of this, or change the numerator and denominator. So this is the solution. Okay, we'll stop here. Only a few problems on, integrals, Laplace multiplication and division by t is over. Then Laplace on derivatives and Laplace on integrals. A few problems we have. All right, I'll stop here. We covered a lot of ground. It needs practice. So please practice and come for the next class.